Optics of thin films. The phenomenal growth of thin film research and development owes much to the stimulus provided by the early utilitarian interest in the application of optical films in mirrors and interferometers. The considerable theoretical and experimental investigations on the optical behavior of thin films deals primarily with optical reflection, transmission, and absorption properties and their relation to the optical constants of films. As a result of these studies, complex multi-layer optical device systems with remarkable reflection, anti-reflection, interference, and polarization properties have emerged for both laboratory and industrial applications. This section outlines the basic relations for the reflection, transmission, and absorption of light by single and multi-layer films. We begin with an analysis on the propagation of electromagnetic waves through optical films. The propagation of a planar, monochromatic, and linear polarized light wave in a medium can be described by a complex description of the electric field intensity as E equal to E0 exponential I 2 pi t over t minus 2 pi n z over lambda, where E is the momentary electric field intensity, E0 the amplitude of the electrical field, I the imaginary unit, t the period duration, lambda wavelength of the light wave, z the local coordinate, and n, which is n minus ik, the complex refractive index of the medium, and small n the refractive index of the medium, and k the extinction coefficient of the medium. The electrical field intensity E and the magnetic field intensity H are coupled over the so-called optical admittance Y with one another as H equal to Y times E. The optical admittance of a medium can be calculated from the complex refractive index N of the medium and the admittance of the vacuum Y0 as Y equal to N times Y0, where Y0 equal to square root of epsilon 0 divided by mu 0. Except for the proportionality factor and dimension factor Y0, the optical admittance Y is equal to the refractive index of the medium concerned. Now, if a planar light wave under an angle alpha strikes any boundary surface between two media with different refractive indices, then the wave is partly reflected and partly passed. Reflection and transmission can be calculated from the condition that the components of the electrical and magnetic field intensity tangential to the boundary surface at the passage through the boundary surface must be constant. These two tangential components are connected with one another over a modified optical admittance eta, that is H equal to eta times E. And the reflectance at this boundary surface can be shown to be R equal to modulus of eta 0 minus eta 1 over eta 0 plus eta 1 the whole square. Here, the indices denote the incidence medium 0 and the emergence medium 1. The tangential electromagnetic fields at two adjacent boundary surfaces A and B are continuous and are related as matrix EH equal to matrix M11, M12, M21, M22, which is equal to matrix cos delta I over eta sin delta I eta sin theta cos delta multiplied by matrix EB HB. The components of the matrix depend only on the properties of the film at both boundary surfaces. This is therefore also called the characteristic matrix of a film. In this equation, the phase factor delta calculates to be delta equal to 2 pi n d cos alpha divided by lambda, where n is the complex refractive index of the film, d the geometrical thickness of the film, and alpha the propagation angle of the light in the film relative to the axis of propagation. In the case of a film system with several layers, the field forces at the entrance of the layer system with the help of E0 H0 and at the exit of the layer system at the entrance of the substrate ES HS can be connected by multiplication of the characteristic matrices of all layers with one another. Thus, it is valid that E0 times matrix 1 Y equal to product from R equal to 1 to M of matrix cos delta R I over eta R sin delta R I eta R sin delta R cos delta R multiplied by matrix 1 eta S times ES. Here, Y is the entrance admittance of the film and eta S is the optical admittance of the substrate for the tangential field components. Alternatively, this equation can be written as matrix BC equal to M times matrix 1 eta S, with M equal to the product M1, M2, M3 to MM and Y equal to C over B. We see that the characteristic matrix M of the total film system is equal to the product of all characteristic matrices of the single films, that is M equal to product of M1, M2, M3 up to MM. The reflection of the film system can be calculated in analogy to the reflection of a boundary surface between two homogeneous media. In the case of homogeneous media, we already have seen that R equal to modulus eta 0 minus eta 1 over eta 0 plus eta 1 the whole square. Inserting the admittance of the complete film system in place of eta 1, we will get the reflectance of the film substrate system as equal to modulus of eta 0 times M11 plus eta S M12 minus M21 plus eta S M22 over eta 0 times M11 plus eta S M12 plus M21 plus eta S times M22 the whole square. In the case of absorption-free films, the phase factor delta of a layer is given as delta equal to 2 pi n d over lambda 0 cos alpha times lambda 0 divided by lambda, where n is the real part of the complex refractive index n, With absorption freedom, we have n equal to small n. The product of the refractive index n and the geometrical thickness d is called the optical layer thickness nd. The optical film thicknesses are frequently indicated relative to the reference wavelength lambda 0. That is the reason why we have inserted a lambda 0 in the above equation for the phase factor delta. We now try to understand the characteristics of a single layer of thin film on a substrate. The array elements of the main diagonals of the characteristic matrix of a single film is given by this expression. Note that M12 equal to M21. For a given optical film thickness of a film Nd, the phase delta depend on the respective wavelength as delta equal to 2 pi Nd over lambda 0 times cos alpha lambda 0 over lambda. In practice, those wavelengths are of special importance for which the optical thickness of the film corresponds to a multiple of lambda 0 divided by 4 and or lambda 0 divided by 2. With these wavelengths, the reflection and or the transmission curves of the layers exhibit extreme values. For the preceding analysis, we assume perpendicular incidence of light. In that case, the optical admittance of the material can be replaced by the refractive index, that is eta r equal to n1. We will now consider a layer of thin film which is having a thickness of lambda 0 divided by 4. In that case, the characteristic matrix is m lambda by 4 equal to matrix cos delta r I over eta r sin delta r I eta r sin delta r cos delta r, which is equal to matrix 0 I over n1 I n1 0. On a substrate with refractive index ns, the reflection equation is r lambda by 4 equal to modulus n0 minus n1 square over ns divided by n0 plus n1 square over ns the whole square. That means with lambda by 0 layer, in accordance with the above equation, depending on the respective refractive index of the layer, one can generate reflection increases or reflection reductions. This figure shows the spectral reflection curves of some lambda 0 by 4 layers with substrate refractive index ns equal to 1.52. Curve 1 corresponds to the reflection of the uncoated substrate, and curve B corresponds to a thin film layer having refractive index n1 equal to 1.38, and curve C is that of a thin film having refractive index 1.233, and curve D is that of a film having refractive index n1 equal to 2.30. We see a quarter wavelength thickness coating of a material on a substrate diminishes or enhances its reflectance to a value given by the above equation, depending on whether refractive index of the film is less than the substrate refractive index or refractive index of the film is greater than the substrate refractive index, that is n1 less than ns or n1 greater than ns. This principle is utilized for the construction of anti-reflection or reflection coatings. In general, for anti-reflection coating, the refractive index of the film has to be the geometric mean of the refractive index of air and that of the substrate. That is N1 equal to square root of N0 times Ns. This figure shows the use of anti-reflection film on a pair of spectacles. We will now discuss about thin films having a thickness equal to lambda 0 divided by 2. In this case, the characteristic matrix M lambda by 2 turns out to be matrix -1 0 0 -1. On a substrate with a refractive index Ns, the reflection equation turns out to be R lambda by 2 equal to modulus N0 minus Ns over N0 plus Ns the whole square. That means reflection of the lambda 0 by 2 layer is independent of the film refractive index, that is N1, but depends on the refractive index of the uncoated substrate. The theory that we so far has been discussing can be used to create interference filters. Optical filters based on the phenomenon of interference in thin films are called interference filters. According to their characteristics, these can be divided broadly into two categories. Band filters. Band filters have a region of transmission bounded on either side by regions of rejection or vice versa, and are accordingly called band pass filters or band stop filters. Both can be either of wideband or narrow band type, and band stop or rejection filters are simply reflection coatings. The second category is edge or cutoff filters. Edge filters are those whose primary characteristic is an abrupt change between a region of transmission and a region of rejection. These can be either short wave pass or long wave pass. We will now discuss the theory of all dielectric reflection filter, which can be used as a band pass filter. We already have seen that the high reflectance of a lambda 0 by 4 layer is due to the phase agreement of the beams reflected at the two surfaces. The same relation can be maintained in a stack of alternately high and low index lambda 0 by 4 films. With such a stack of odd number of dielectric films, reflectance very close to 100% and with negligible light loss can be expected. The usual arrangement has high index lambda 0 by 4 layers next to the substrate in odd number positions and is denoted as HL, 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 etc. The calculated maximum reflectance at lambda 0 by 4 for Z number of layers in air is given by R equal to modulus NH to the power Z plus 1 minus NL to the power Z minus 1 times NS over NH to the power Z plus 1 plus NL to the power of Z minus 1 times NS the whole square. Here, NH, NL and NS are the high, low and substrate indices. Z layers of the dielectric are equivalent to a single layer whose effective refractive index is equal to square root of nh to the power of z plus 1 over nl to the power of z minus 1. This figure shows the spectral characteristics of such a multi-layer stack. On the x-axis we have plotted lambda 0 divided by lambda, and on the y-axis it is the reflectance in percentage. In this figure, 3, 5, 7 and 9 indicate the number of layers of the thin film on a substrate. It is clear that the magnitude of the reflectance increases with the number of layers. The number of sideband oscillations outside the high reflectance zone also increases with the number of layers. The spectral width of the high reflectance zone is a function of the ratio of the refractive indices of the involved films, and there are a couple of practical ways to extend it. One is to select materials with NH and NL that are higher and lower. Another is to broaden the basis of design to include several wavelengths. In that case, the dielectric stock would be composed of staggered layer of thicknesses so that consecutive maxima would overlap. That is, we would design the system to have multiple maxima and finally, when these multiple maxima overlap, we get a broad reflectance curve. The cold and heat or dark mirrors are an extension of the reflectance system that we have just seen. The cold and heat or dark mirrors are selective reflection filters. Selective reflection over a limited spectral region may be obtained by depositing interference combinations of dielectric and metal films on an opaque mirror or all dielectric lambda 0 by 4 high-low layers. The cold mirror. A cold mirror consists of a semiconducting substrate, germanium for example, which is transparent to infrared when used as a substrate for a lambda 0 by 4 HL stock and reflects in the visible spectrum as you see in this figure. This construction forms a cold mirror since it reflects the non-heating visible light and transmits the heating infrared. The spectral characteristics of a cold light mirror are shown in the figure. It has high reflectivity for visible light, but a high transmission for IR radiation. In addition, the first film on the glass should be a material having high reflectance in the visible and transmitting in the IR, example germanium or silicon. A few alternating lambda 0 by 4 amplifying film layers on top of this help achieve the high reflectance over a suitably wide visible bandwidth. If semiconducting films which are transparent to infrared are used, The mirror combination has negligible reflection in the visible and high reflection in the infrared. Such a system is called a heat mirror or a dark mirror. Heat or dark mirrors have characteristics that are inverse to those of cold mirrors. These are used in energy-saving applications such as home window panes. Window panes, when coated with heat mirrors, would reflect heat back into the house in the winter. In the summer, the window could be reversed so that the coating could reflect the IR from the sun and help provide interior cooling.